guys, in this video I'm gonna introduce you some interesting concepts, which is pointwise convergence and uniform convergence. Remember, we have seen the convergence of a sequence of real numbers. That is, so in which case can we say that a sequence is convergent? Is that, well, suppose xn is a sequence of real numbers in the metric space xd, and we say xn is convergent in X if for any epsilon larger than 0 there exists a natural number n such that the distance between xn and x0 is a number that the sequence is converging to. The distance between xn and x0 is smaller than that epsilon for any n larger than the capital N. And another thing you have to pay attention is that the number that the sequence is converging to must be contained in the set X. So in a sense, the point is if you can find a natural number n. So if for any epsilon you can find a natural number n, then a natural number n such that the sequence satisfies the condition that xn and the distance between xn and x0 is smaller than epsilon, then you can say that xn is convergent. So the point is if you can find such n. So if we put the situation into a metric space not for real numbers, but in the case that we are talking about the sequence of functions, like given in the metric space in say 0 to 1, d1 or dl1 or dl the positive infinity, like this distance. It's the same for a sequence of functions, but the point is now the elements or the elements that we are going to compare the distance is now become the elements becomes functions that are the functions which are continuous functions, and the domain is from 0 to 1, and the distance function might be different. It depends on what distance functions. What distance function is the metric space based on? So this is what we call convergence of a sequence of like numbers or functions. But what if we want to get more information about the convergence? Is the convergence is there any higher or stricter criteria for convergence? Then we say we have actually pointwise convergence or uniform convergence. So let's first see the definition of these two kinds of convergence. So first of all is pointwise convergence. From the name of the convergence you can see it's pointwise, so there must be something about the point you choose, right? So still we are given a sequence of functions fn, and the definition is going to be for any epsilon larger than 0 there exists for any epsilon larger than 0 and any x in the domain capital X, there exists n, a natural number n such that the distance the distance here must be d1 distance, which is if you are given x and y 2 points, then the distance must be x minus y. Take the absolute value of x minus y. So fn minus f is a function that you want to show fn is converging to. Fn minus n, take the absolute value of it, must be smaller than epsilon for any n larger than the natural number capital N. And if we are going to use it in a neighborhood language, that will be for any epsilon larger than 0 for any x in the domain x, then there must be a natural number n such that Fn is contained in the ball which centered at F, and the radius of the ball is epsilon for any n larger than n, right? Because in the previous definition we said Fn minus F is strictly smaller than epsilon. Then you say actually when n larger than the natural number, all the functions Fn must be contained in the ball centered at F, right? So then we say Fn converge pointwise to F. Here still we are going to find a natural number, and it depends on if you can find such n. If you can find such n, such that is the functions in the sequence satisfies the conditions, then you may say that the function converge pointwise to some function f, right? But what about uniform convergence? And what's the difference between uniform convergence and pointwise convergence? Okay, we say a function is a sequence of functions is uniform convergence, convergent to a function f if we'll say for any epsilon larger than 0 there exists an n, natural number n, such that for any x in the domain x, Fn minus f, take the absolute value of the subtraction, then take the absolute value of the difference of Fn and f. The absolute value is smaller than epsilon for any n larger than the natural number n. Then the sequence of functions Fn converge uniformly to f. You see, actually, the essence is still to find a natural number n, but the difference between pointwise convergence and uniform convergence is that the pointwise convergence, the natural number n is like can be one-to-one correspondent to x, the x you choose. So that is, you first fix an x in the domain of the sequence of functions, and for that x you fix, you can find a natural number. And if you can find such number, then the sequence must be pointwise convergent. But for uniform convergence, you cannot fix a point x. That is to say, the natural number n you find must be like universal. Alright, it's like well, say in the pointwise convergence, you might like find x1 and x1, for x1 you can find n1, x2 n2, and so on. You can find like, actually there are infinitely many x in the domain, and you can find infinitely many n corresponding to x, right? And for uniform convergence, first of all, this must be satisfied, right? But that's not enough. The n you find, the natural number you find must be like, the natural number you find must be like the minimum. I'm sorry, not minimum, the maximum or the supremum of all the n1 to like nt, right? Because that must be satisfied for all x. That is what we say uniform convergence. So another way to say it is that in the pointwise convergence, the natural number n can be a function of epsilon and x, right? Because you are going to find n when you are given epsilon and x, right? This is pointwise convergence. And for uniform convergence, the natural number n you find can only be a function of epsilon. It cannot be a function of x. I think in my opinion, this is this would essentially differentiate the pointwise convergence and uniform convergence. The point is the function n, what variables it depends on. Okay, so this is the definition of pointwise convergence and uniform convergence. Now let's see some examples. The first one, so suppose we're given a sequence of functions which are from 0 to 1 to r, real numbers. So the function is given by -1 to the power n times x to the power of n. Okay, given such functions, honestly, I don't have any clue of like how to get if it is pointwise convergence or uniform convergence. So the first thing I did is to like draw some pictures. Suppose n is equal to 1, f1 is equal to -x, and f2 is equal to the square of x, and f3, f4, f5, blah blah blah. You can draw some like even more, but I think that 5 functions are enough for us to find something. Okay, so when n is equal to 1, you get -x, which is this line, the line segment, right? And f2 is x squared, that is a line like this, and f3 minus x to the cube, this line, and f4, f5. You see when n is like even, then the function must be even, right? The value of the function must be even, and it is like getting closer and closer to 0, to this line. But this is the case when x is not equal to 1, right? Because you see, when x is equal to 1, the function fn is either 1 or -1. So when x is smaller than 1, you see, when n is even, the function is getting closer and closer to 0. And when n is odd, the value of function is negative, but it's still getting closer and closer to the 0 to the x-axis, right? So actually, if x is smaller than 1, the function from 0 to 1, which exclude 1, I think it's easy to say that the sequence of functions in this domain is a uniform convergent sequence, and it is also pointwise convergent. As you can see, if you fix a point in from 0 to 1, then the value of the functions are getting closer and closer to 0. They are actually getting smaller and smaller. So if you are for example, if you fix x here, 1/2, and you like choose a epsilon that this large, so this 0 minus epsilon, and this 0 plus epsilon, and this is 0 minus epsilon. And you can see when n gets larger, the value will be only like getting closer and closer to 0. That is to say, these values will be contained in this interval, right? So it is pointwise convergence, and actually it is also, but it's pointwise convergence. That is when x is smaller than 1. But when x is equal to 1, it's not convergent at all, right? Because the value of the function is either 1 or minus 1. It's like oscillates, so it cannot be convergent. So to sum up, if we are given a function like this and a function like this and the domain is given by 0 to 1, the function itself, the sequence of functions is not pointwise convergent, and it's not uniform convergent. So a thing that I forgot to mention is that a uniform convergence actually has like stricter criteria than the pointwise convergence. So the thing is, if a sequence of functions are uniform convergent, then they are the sequence is also pointwise convergent. But pointwise convergent not necessarily can conclude that uniform convergence. Okay, so that is to say, if a sequence of functions is not even uniform, it's not even like pointwise convergent, then it cannot be uniform convergent, right? Actually, we have another like useful theorem, or it can also be a criteria for you to check a function is not uniform convergent. But first let's say another example. Fn x equals to x over 2 to the power of n. So I don't think we need to draw like pictures or graphs of the functions, because you can easily say that the sequence of function is converging to a function which is 0, the 0 function. But we still need to check if it's set by definition, if it satisfies the condition that is equivalent to saying if we can find such natural number n. So we take the absolute value of fn and the 0 function, and it's equal to itself, x over 2 to the power of n, right? And since we know x is smaller than 1, x over 2 to the square of n will be smaller than 1 over 2 to the square of n, right? And we are trying to find a natural number n, and we know that the functions after n, that is to say, n larger than the natural number, the functions must satisfy that criteria. So we know that n is larger than capital N. So that is to say, 1 over 2 to the power of n is smaller than 1 over 2 to the power of capital N, right? We wanna show that this part is smaller than epsilon. So we are going to try to find if we can find such n. If we can find such n such that the equality exists, or the equality holds, then we can show that the function is actually uniform convergent, right? Because here we did not fix an x. The x is the natural number n is like universal for all x, right? Okay, so it's quite natural that we can say that n is smaller than log 1 over 2 to epsilon, but this is not the end. Many people just stop in this step, stop from this step, but you see, actually, what is the graph of log 1 over 2 to epsilon? That will be like this. So if epsilon is like larger than 1, n is smaller than a number that is smaller than 1, then it's not possible because the n is a natural number. It cannot be smaller than n, right? So this only holds when epsilon is smaller than 1, and of course it's larger than 0 because we are taking a positive epsilon, right? So what happens if epsilon is like larger or equal to 1? When epsilon is larger or equal to 1, you just take n is equal to 0. This is enough because 1 over 2 to the power n of n will be smaller or equal to 1, right? So if epsilon is larger than 1, then you can take n equal to 0 or n equal to 1 or anything. Right, so we actually find an natural number n or a function n dependent on epsilon, right? So we can show that fn is the sequence of functions fnx is uniform convergent. So these are 2 examples, and the theorem I mentioned that is also another method to check uniform convergence is that if we are given a sequence of functions fn, and we know if we know that fn is convergent to some functions, we know we want to know what kind of like characteristics or what kind of function the sequence of functions is converging to. What kind of function is that? So suppose the sequence of functions fn are continuous, so the functions themselves are continuous, and if we're given fn converge to f uniformly, then we can say that f is continuous. So you can think of this theorem from another perspective. That is to say, if fn are continuous, the sequence of functions are continuous, but the function that the sequence is converging to is not continuous, then fn must not converge to f uniformly, right? So if we are given a sequence of functions like this is also like a classic situation we will consider. Functions. So this is n equal to 1, n equal to 2, 3, 4, 5, to n equal to t. Like the sequence of functions fn x is converging. Looks like it converging to 0 if x is smaller than 1, and 1 if x is equal to 1. This is pretty similar to the example that we talked before. So you say this function must not be the convergence must not be uniform, right? Because you say fn are continuous, right? And in fact, this is a function. The sequence of functions can be stated like this: x to the power of n. So fn is continuous, but the function it converges to. So this is f. It's not continuous, right? So the convergence cannot be uniform, but you may like verify yourself that the convergence is actually pointwise. So back to the example that we talked before, if we're given a function like a sequence of function like -1 to the power of n times x to the power of n. This function is not, this sequence of functions is not uniform convergence. It can easily verify by using that theorem, that is to say, fn, the sequence, the functions in that sequence fn are all convergent, right? But the function, the sequence of function is converging to is not continuous. Actually, I wouldn't say the function that the sequence of functions is converging to, because you see when x equal to 1, when x equal to 1, it's the function that we're trying to show that fn is converging to has two values, which is 1 and -1. It is not even a function. If it is a function, when x equal to 1, it must have only one value. So I don't think this is a function at all. So naturally it cannot, obviously it cannot be uniform convergent, right? So I think this is what I want to talk about in this video about uniform convergent and pointwise convergent. Actually in uniform convergent we have a lot of other like theorems discussing what kind of function that the f is. I mean, the function is the sequence of functions that are converging to. So what if the sequence of functions are all integrable? What if the sequence of functions are all differentiable? What happens to the function that they are converging uniformly to? We might talk about that in the next video. So see you in the next one.